photon mapping. So another global illumination technique is photon mapping. So let's assume we have again a camera, screen, some kind of a scene geometry and a light source. Now the first step in photon mapping is the construction phase. Here we actually shoot photons out from the light source. We find the paths of those photons with ray tracing and see where they intersect with the scene geometry. And we might also reflect them around a bit. We're going to save the photons' directions and energies when they intersect with the scene geometry. And this creates us this photon map. So this is basically a map of all these photons that were shot from the light source and then stored when they intersected with the scene geometry. The second phase is the gathering phase. So now we shoot a ray from our camera through our screen for each pixel and we find the intersection point, just like with regular ray traced rendering. Next, we're going to have a sphere that includes some closest n photons from the map. So we're looking for some n photons that are close to the intersection point, and well, these will lie in some specific sphere. At that point, when we're trying to look up the photons, some space partitioning algorithm like an octree will speed up finding those closest photons. This means that when you're creating the photon map, you should already consider what space partitioning technique are you going to use and where are you storing those photons. You can store them in an octree that will make fetching them later much easier. Now what happens next is that we consider all of these photons, some n of them, that were the nearest to the intersection point, and we divide each of their contributions with the area of the encapsulating sphere. The logic here is that if these photons were close to the intersection point, then they represent a more accurate illumination value. But if they are more further apart, then the contribution is less accurate, so we divide by the area of the encapsulating sphere. And here is an example of a photon map. This was created by Hendrik Eerikson as a high school project, and it was implemented in Python. The light source was somewhere around here, and photons were shot out onto the scene from the light source. The scene also had differently colored walls, so the back wall was green, the right wall was red, and the left wall was blue. This was a red sphere, and this was a refractive sphere. So when light photons intersected with this refractive sphere, they actually refracted into the glass and then came out the other end, creating this interesting focused shape on the ground. Now this picture shows the photon map itself, the construction phase. When we go to the gathering phase, the result will look like this. And here we can see how the shape on the ground where the light has been focused actually looks. This is called caustics. And you can see similar effects when you render wavy water, where waves refract and focus the light, let's say on a seabed. Or if you have a glass of water, or even an empty glass, then light still hits it, refracts it, and then creates these interesting focused patterns on the glass or on the surface that it's on. And this is actually where photon mapping is really useful. It can be used independently for just calculating the caustics. So from this video, you should understand photon mapping, its construction phase, where we shoot the photons out of a light source and store them, its gathering phase, where we now render the scene with ray tracing and gather the contribution of nearby photons to calculate the final color. You know that space partitioning structures can be used to store and fetch these photons, and you know that photon mapping is very useful specifically for these concentrated refractive optical effects like caustics.